It is very tedious to get through all the problems. And I think I'm hoping I'll move a little bit faster now that I've taken the time to just like slow down and try to build an intuition for how to approach the problems. But it was breaking my brain. So I think I'm finally understanding a few key things.
This is the hardest intellectual thing I have ever done.
Probability has never been my forte, hence why I wanted to do this book club, but it's complicated.
Yeah, I did a politics degree and I did some social research methods as part of that, and I did some post-grad social research stuff as well, and it's definitely harder.
Yeah.
Yeah.
Yep. It's only going to get harder as the book goes on, I think.
Don't say that. Don't say that. I'm trying to kid myself that it's going to get easier.
I don't know. Maybe at least like figuring out how to set up the problem will hopefully get a little easier. I think that's where my confusion has been a lot of times, is just thinking through how to set it up and whether it's like permutation versus combination, and just like trying to organize my mind over how those things are different and how ordering, if you need ordering, if that changes it. And I just tend to have the wrong instincts quite a bit. So we'll see.
Well, my last formal maths training was GCSE, which is to age 16. I don't know what they have in the States.
Yeah, we have what's called like advanced placement, which is like a college board thing. So you can get college credit for certain things when you're in high school.
I'm kind of thinking that I should have done maths A level, which is the 16 to 18 bit.
Yeah, I haven't taken, I'm in the same boat. So I've had to review a lot of math for this course too. A lot of the calc review that was on the, like one of the handouts, I was like, oh my gosh, I don't actually know if I ever learned the Taylor series, and it's very confusing, and I'm sure it's going to be important. Yeah, I haven't had any formal math training since since high school. Yep.
It's very difficult. Yeah.
Yeah.
I haven't actually cried yet, but I might do. Before the end of the book, that's my aim, not to cry, you know.
I haven't cried either, but I've definitely cussed more than my more than my usual daily allotment, I think.
Because I've seen some of the videos that is done, and they sort of make sense.
Sort of, but I think he goes through things a little bit too quickly sometimes, and I find that I think a little bit differently, I think, than he does. So I've found a few other videos that I found helpful. I found one that finally explains like the Newton Pepys problem. So I'm like, oh, I think I finally get that. So
that's the thing. He's a professor at Harvard. He's going to understand it. That's what they do.
Yep. Okay, well, it's looking like maybe it'll just be me and you today. So should I just share some slides quick?
Yeah.
Let's see. Well, I gave Quarto presentations a shot.
This is like R Markdown, but really advanced and fancy, isn't it?
I actually really like it, but I found that my biggest problem was with just the formula formatting. When you want to have, all of your formulas in there, it got kind of complicated with things that it accepted versus didn't accept. So I spent a lot of time trying to find the mathematical notations and that kind of stuff. So
is it called LaTeX? Is that
I think it's based on that, but it's a little bit different depending on whether you're an R or Python. And so I would find some Stack Overflow suggestions for issues that I ran into, and they weren't quite the same syntax for R. So it was a little problematic. Hang on, sorry, just moving my windows around so I can share. Okay.
Ooh.
All right, can you see the slides?
Yeah.
Is there a better way to do it where it's like more full screen and you don't see my browser?
Oh, there we go.
There we go. Okay. So, like I said, sorry, I was hoping to move through this book really quickly, but I think I need to slow it down at these early ones. So I just kind of put a few slides together as I was thinking through how to approach some of these problems. And these were a few of the ones that were they weren't even the problems at the end of the chapter. These were problems that he worked through the solution in the text and I still didn't get it. So
Yeah.
I had to break it down a little bit. And this was something that he included actually before we get into the practice problems. I have a few slides of just like review and consolidation of some of the formulas that we're going to be drawing from a lot in the book. He kind of put together a table like this in one of the YouTube lectures that's been posted, but I didn't see it anywhere in the actual book of the text.
Mm.
So I find this like a helpful reference to have in mind, just to remind yourself like, okay, like what is the scenario that I'm looking at and how can I categorize what I'm trying to do and use formulas that exist and hopefully start getting better at the pattern recognition of like, what are we actually trying to answer with the approach? So, so like the ordered, when order matters, we're essentially, the term that's used for that is a permutation. So like some of the examples that were given in the text were how you could arrange different letters in a word, or how you could select different combinations of people where the order does matter. And so if you're doing those selections, but you're making a selection, then you're putting that selection back into the pool for every subsequent, choice that you're going to make. Then you have, sorry.
Yep. Yeah. So with replacement, I'm just following along here.
Yep. So then you would have, sorry, can you see my cursor on the screen too?
Yeah. Yeah.
Okay, cool. So then you would have n to the r total number of possible outcomes for that. But if you aren't replacing those things, then you basically have like this little correction factor where if you have a total of r selections that you're making, most often in the text he's putting a k, but here it's an r, then you have to correct for the number of choices that you've made as well. So if you're not replacing those things, then it's n factorial. So your first choice could be any of n things. Your next choice could be any of n minus 1 things, and so on. But then to account for the possibility of double counting, you subtract r or k from the n and divide by that here. This unordered with replacement is one that was more complicated. And not all that intuitive. And I think maybe it would be worth at some point us going through like how this was computed, just so like we really understand it. But
one of the things that I found helpful when I'm kind of like hitting my head against the table is it, because basically all those letters, all the algebra kind of stuff, I don't really get. So what I like to do is just put very simple numbers in, and then it makes more sense.
Yep.
So kind of like n choose k, start off with 2 for n and 1 for k, and then do the factorials out of that, or maybe 3 and 4 if I want to get really advanced. And that kind of like puts it into kind of like something that I can understand a bit more easily.
Yeah, for sure. So this one is a more like kind of complicated logic behind how this one was derived. So yeah, I think not today, but maybe a different time if this comes into play and is being used, we could maybe break it down a little bit. But for now, this is just the general form that it would take. Although he made a point of noting that this is a very special case that often violates the naive assumption of probability. So to use it with caution. I don't really know exactly what he meant by that at this point, but I'm sure we'll find out what would be scenarios that would violate.
What he's basically saying is that there's a booby trap there, but we're not going to say where exactly it is.
Yeah, we'll find that booby trap, I think, in a few lectures probably. And then if we want to, this is kind of the bottom right one here is kind of the most, probably going to be the one, our bread and butter that we're using the most is if we have a group of n and we're making k choices and the order doesn't matter. We just want to see how many different ways are there of us to choose k items or r items from a group of n things, and we're not going to make any replacements. And so that's kind of, so far in a lot of the practice problems, this has been one of the most
the choose
commonly
function
used.
in R. I like the choose function in R.
Yeah, that's been super handy. I'm glad that
Yeah.
it goes through some of the R practice for sure. So this one here, this is basically the same thing. This is the n choose k one from down here, but it's one of the few that for whatever reason has its own very special name. So I just thought it would be helpful just to remind ourselves, like there's a bunch of different syntax for how this is described, depending on the context. You can see it as like C N K or N choose K, or most commonly in this
Isn't
format.
it nuts how they have like all these different things for the same thing?
Yeah.
Yeah.
So it gets very confusing. Yeah, so I thought it'd be helpful just to remind ourselves that we can see it in a bunch of different ways, but it's saying where we're choosing K objects from N total items and we're not making replacements and the order doesn't matter. This is the general formula for that. And so sometimes it's helpful just to kind of plug and chug into the n factorial, into this middle kind of formulation of it, but other times you can cancel out terms more effectively if you put it in this configuration. So yep, so a reminder, this calculation assumes that the order matters and that each object K is unique. So the labeling of objects is another important kind of conceptual thing. As we think through this, if we're like picking balls out of a bowl, we have to, in some situations, we need to make the assumption that each of those, even if we can't tell what that ball is, that it's different from the others, that it is unique. It's a unique experiment. And so we have to kind of like mentally label those things.
Yeah.
On this slide, this is just another reminder of just some of the helpful identities that ideally we won't have to memorize. Like I'm hoping that we'll build an intuition and just be like, oh yeah, duh, that makes sense. But for now, like I have to, this one in the middle in particular, I don't quite find super intuitive yet. This one makes sense that if you choose, 4 items from a group of 10, you have the same number of possible ways of doing that as choosing 10 minus 4 items from 10. Because if you choose 4, then you by default have chosen the other 6 if you're not making replacements. So that one kind of makes sense. This one is a little bit more complicated to me, and I'm going to see if I can. Do you have an intuition for this one yet?
To be honest, no. It's the answer to that. I need to spend some more time with Khan Academy and helping me understand the formulas a little bit more as well.
Yeah, I watched a few of those too, especially on some of the trying to remember some of my basic calculus. Yeah, so this one, I don't quite know yet how it's going to come into play. This might be a useful one to just kind of to know, and it might help us solve more complicated problems in the future. But as far as the intuition, it's a little bit more complicated. I think it's saying like, yeah, I'll have to go back. I think in one of the lectures, he explains some intuition behind this, but I clearly didn't absorb it fully enough to speak it again now.
The thing is, these are really complex things because you can watch the video, you can read the book, and after another 15 attempts at that, then it kind of goes in. It's kind of like you read it the first time, and you think you understand it, but you don't really.
Yeah, that's kind of where I'm at with it too. So I think hopefully next week, I just need to spend some time in it every day and annoyingly go through more of the practice problems because it's breaking my understanding, or really testing the limits of my understanding, I should say. Yeah,
I mean, that's the thing. They're horrible, but I think the practice problems do work. I think that's why they put them all in.
For sure. This identity down here is one that does actually make sense to me, even though like looking at it, it looks a little bit confusing, but this is kind of saying, and one of the practice examples in the book was saying, imagine that you have 2 different groups of people and they're distinct in some way. Maybe you have different numbers in each of those groups and you want to choose K out of those 2 combined groups. Well, that's kind of the same thing as saying, look, well, how many, let's break up your number of choices into some sub choices where you have, well, K equals, J. If we say that we're going to choose J such that J is less than the total number of K choices, we're going to choose that from one group, and then we're going to choose K minus J from the other group. Those all have to sum up to be the same number of total choices that you made from the combined groups. So it's as if you're sampling from them separately, but then the total number of choices still has to add up to what you set in the beginning. So I think the example that was given is if you were like choosing, you know, students, choosing from a group of 10 juniors and 20 seniors or something, and you have to choose 5 of them. You know, if M is the 10 juniors, then you're gonna, let's say you choose one of them. Well, then the other part of K has to be made up from the other group. So that would be K minus, so it'd be 5 minus the 1, which would be 4. So that was not the most eloquent way of saying it, but does that make sense?
Let me try and put it in a way that I understand, which may not be correct, but I'll give it a go. So if you have 2 football teams, and you are picking your 6 favorite players across those 2 football teams, and you pick 3 from one, you have to pick 3 from the other. Is that what it's saying?
Yeah, pretty much. Yep.
Cool.
Yeah.
Some of that went in. Well
Yeah.
done.
Let me see. Can I hide this thing? It's kind of in the way here. So now I just have a few examples that I kind of took my time in going through that I initially got very wrong in my assumption of what they were. This was on one of the homework problems. Actually, the website has, you know, a bunch of PDFs of actual homework assignments and the solutions for those. And this one was broken up into actually like equality kind of question, where you had to say, well, what's greater, the probability of the total after rolling 4 dice to be 21 or for it to be 22? But I figured let's just walk through one half of that problem first. And so I really struggled with how to set up this question. And I think still problems like this are a bit of a challenge to my understanding of probability, because I still think of probability in the very like naive way. Like, we have 4 dice. I know that each die can be one of 6 outcomes. So I'm comfortable with that kind of math and like the total number of outcomes. I get it. But now it's like, well, we have some options where there's several different ways we can total that sum to be 21. I can write out a few of the options, be like, okay, like, but now how do I figure out the math of like how many different ways there are of doing that? And so, navigate here. So if we kind of start with that approach and saying, okay, well, we have 4 dice, the minimum value that they could take when we roll all 4 together would be 4 1s. The maximum would be 4 6s. So we know we can get a range of values from 4 to 24. So 21 is kind of on the high end of that. So we know we're going to need at least one, like multiple 6s in it. So this part is kind of a little bit more of like just brainstorming and doing some mental math to figure out like what are the different numbers I can add together to get 21. So it'd be easy to, I guess, miss them in this particular example, but thankfully there's not too many. We can get 3 6s and a 3. We can get 2 6s and a 5 and a 4, or we can get 3 5s and 1 6. And then this one in the middle here, this 2 6s and a 5 and a 4, for me was the most confusing to figure out how many ways you could get that. But basically, this is the solution that I think I understand the most. And this is kind of one of these like N choose K types of problems. So I found my instinct was to go to the like 1/6 probability to roll a 6, 1/6 probability to roll another 6. And I was trying to figure it out that way. But if you kind of shift your thinking into looking at as the N of 4 dice instead, and you're choosing a certain number of those 4 to take on a certain value and to permute that, then this problem becomes a lot simpler. But the intuition to frame the problem in that way is where I personally really struggle. So this is the explanation. Sorry.
This is sounding like you're a genius. Yes, keep going.
No, I struggle with this, and like I kind of get it at this point, but I guess I don't get why it works. Like I get this math, it checks out, it works, but I still like there's something that hasn't completely clicked for me yet. But basically, if we think of the situation where we have 3 6s and a 3, we're trying to figure out what are the number of ways that we could roll the dice that could happen. And so in essence, like I'm guessing this is going to come into play later when we learn more about degrees of freedom. But if we have these 4 numbers, we know that we only have one number that can vary in its location, but it has 4 places where it could be. So we have 4 dice, and we're choosing which one of them is going to be the 3, and then the rest are going to be a 6. And I think perhaps part of my confusion with this is at this point, we're not computing any probability. So we don't have to be like, well, how probable is that? We're counting what are the number of configurations that allow this to happen. And then later we're going to divide by the total number of possible outcomes in order to get probability. But here we're just counting configurations that allow this. So it comes down to a 4 choose 1. So we have 4 possible, and then going back to that formula, we have four dice, and only one of them is going to be that. So it ends up being n is 4, k is 1, and it looks more complicated here, but it's really, we have 4 options, and then once we've made that choice, then it's not going to be any of the other ones. So this boils down to just 4. Like, I think even plugging it in here makes it more complicated. Intuitively, we know we have 4 choices, but it's comforting to put it in the formula and be like, okay, this is the one I understand, and it checks out with that formula. Cool. So then we can go on to the slightly more complicated one, which is where we have 2 6s and we have a 5 and a 4. And so you can imagine that, you know, if we numbered the dice again, so this is where like the labeling comes into play.
Yeah.
These are not indistinguishable trials. Like there are die number 1, die number 2, die number 3, and die number 4. And the order that this happens in is important. So if die number 1 is a 6, die number 2 is a 6, 3 is a 5, 4 is a 4, that's one configuration. But if we flip the order of the 5 and the 4, that's a totally different configuration. And that's another way that we could achieve this. So that's another permutation of these numbers. So because it's only 4 numbers, I actually like wrote all of it out to like make sure that I could like, that this was right.
Yeah, I think I did that with the. I think I don't know if you can see that, but I was doing that with the tournament questions on there. Yeah,
I found that I had to for this one.
Yeah.
I just didn't understand in the text. He didn't write it out in this way. He just wrote 4 times 3 divided by 2, and I was like, what the hell? Like, where does the 2 come from? Like, he skips a few simplification steps that I think for me are really important. But if we break it down in the same way as the first one. In the first one, it was a little bit more intuitive because we were choosing where the 3 was going to be. And now we're choosing where the 5 and the 4 are going to be. Or you could look at it as choosing where the 6 and the 6 are going to be. And then the 5 and the 4 are the other 2. Like you're making your choice that way. So it ends up being a 4 choose 2 type of arrangement. So if you just plug it into this, you get 4 times 3 times 2 factorial over 2 factorial. And that simplifies to 12. And then because this is a simpler problem, you can write it all out by hand, you can confirm that that is in fact the case. But yeah, knowing to set it up like that is the part that for me is still not quite there. But then the 6 5 5 5 is the same logic as the first one. We're choosing where the 1 6 could be, or you could do a 4 choose 3. It's the same thing. That was one of the important identities that we went through, is that 4 choose k, or like n choose k is the same thing as n choose n minus k. So we could think of it as choosing where the 6 is going to go or choosing where the 3 5s are going to go. And it's the same thing. So then to answer this question of like, what's the probability of rolling a 21 when you roll fair dice? It's just the total number of these possibilities divided by the total number of possibilities for all of them. So there's 4, 12, and 4, that's 20. And then to get the total number of possibilities, well, it's 4 dice, 6 outcomes, to the power of 4 dice. Yeah. So it ends up being 0.015.
Fantastic.
Yeah. But yeah, the n choose k, like thinking of it that way, hopefully doing more of these problems will help me just be like, oh yeah, that's obvious. But I also struggled with the birthday problem at first. Did you go through this one?
No. I mean, I went through it when I was reading it, but I haven't done the questions on it.
Okay. Well, I don't know if there's any questions on it. I think it was just given as an example. But when I read through the solution, I was like, where do these numbers come from? So I like took the time to step through this one again. And it's also a very counterintuitive and kind of surprising answer when you hear what the result is.
Really low, isn't it? You think it's going to be like
Yeah.
loads of people, but it's not.
Yeah. Yeah, so I think the question is formulated a little differently. It's like, how many people do you have to have? How many K people do you have to have such that the probability of 2 birthdays of a pair of people, at least a pair of people having the same birthday, is 50%? And like, yeah, most of the time you're like, oh my gosh, like there's 365 days in the year. Like, so if you look at it as like, well, what's the probability of like you having the same birthday as me? That's 1 over 365, right? Well, let me back before I do that. So like I was approaching it from that way. So I'm like, oh my gosh, like it's got to be incredibly low because you're going to be taking 1 over 365 to some power, and that's going to be crazy small. But the truth is you approach it in quite a bit of a different way. And the intuition is the hard part of this. But to get at the logic for this question, it kind of broke it down into like, okay, well, let's like think this through. If we had 366 people, what's the probability of a shared birthday? Do you want to answer it?
It'd be really, really high. It would be absolutely guaranteed, basically.
Exactly. Yeah. Yep. Like it has to be that way. Like assuming we're excluding like leap years and funny business like that. Like if we have a normal calendar year, every person, even if it's mostly unique, every person has one of those 365 days. So if you have more than the 365 days, then you have to double dip and assign one person to another one of those day bins. So what is the probability that random person A or like me and you have the same birthday? So if we hold one of our birthdays steady, what's the probability that you have the same birthday? Well, it's 1 out of 365. So very low. All right. What's the probability that you have a different birthday than me then?
Really, really high.
Yeah, much higher. You have 364 days to choose from. So it's super high. And importantly for like how to approach this problem is like we have to just remind ourselves like, well, this is the complement of this. Yeah. 1 minus 1 over 365 would be the probability of you not sharing the birthday, and then vice versa. So we can solve this problem by, it's too hard to figure out all the possible ways that we could choose 2 people from this group to have the same birthday. So instead we can compute like what's the probability of a shared birthday among these people, and we can compute the complements of that first. But let's start with a small group first, just to like step through how this formula ends up being constructed for this. So what's the probability of a shared birthday among 3 people? So we compute the complement because the complement of not sharing a birthday is the probability. Oh wait, 1 minus the complement of not sharing a birthday is the probability of a shared birthday. So if we have 3 people and we want to know what's the probability of their shared birthday, well, 1 minus like 364 out of 365, right? So the first person has picked their birthday and the other person has a probability of 364 out of 365. And then we also want the second person to have a different birthday. So it can't be the first person's birthday. And also can't be the second person's birthday. So it's 363 out of 365. So subtracting those from 1, you get P equals 0.008. That's the probability of at least 1 shared birthday among 3 people. So that's super low. So, sorry, I just wrote this morning and I've already forgotten what I put on the slides. So, if we think about like just like trying to recognize the pattern that's apparent in this, like because we're subtracting 1 from n in the numerator up here. And so this looks a lot like the n choose k kind of formula, right? For computing what are how we're sampling without replacing, but we're not sampling people, we are sampling possible dates. And I think that's like the intuition that's a little confusing for this is people are trying to compute pairs of people as if you're choosing a person, but you're actually choosing a day. And you're saying the probability of choosing that day and then choosing a different day and choosing a different day. And so that ends up being like the sampling without replacement type of approach. And that's given by this formula where n is equal to 365. So the number of different ways that you can, some of my different formulas didn't work here, but the number of different permutations, wait, is it a permutation or is it a combination? I think it's permutation. No, I'm not so sure.
We need to go back a few slides for it, but anyway.
I think so. We can revisit that one and try to like make sure we use the right terminology. But the number of different ways to assign birthdays to K people is given by this. Unique birthdays to this many people is 365 for the first person. Well, 365 minus that day for the second person. For the third person is 365 minus 3 or minus 2 and so on. And so that ends up, so this, for me, it's a little more intuitive to think of it as like, this is, you're subtracting n minus 1 from each one. But if you simplify, if you minus n or minus k minus 1, that's the same thing as minus k plus 1, just like the flipping of the minus sign. I don't know why, but I find that more intuitive. So this is the general way that you can count the number of possibilities for how to give unique birthdays to K people. So to get a probability from that, we just divide that by the total number of possible birthday arrangements, which is 365 to the K, which I think that's the one thing that we all seem to understand. That one makes sense, 365 to the K. So it ends up being this formula here. So if you, I don't know, do some automation in R, which I didn't get to do because it took me too long to get this far, you can compute what's the minimum K so that this P gets to be 0.5 or higher, and it ends up being 23. And so one of the ways that this, sorry, go ahead.
Okay. It's just the R programming in this book. If someone's never done any programming at all ever, it's a really nice, gentle way into it, because practically all of the programming in there is literally like one line. Usually it's like about one function. It's lovely.
Yeah. Yes. So I think there's probably like a simpler way to arrange this formula so that you can step through various Ks and not have to do a bunch of typing. Because like if you start with K at 1, that's like quite a long factorial, so it gets a little bit overwhelming. Probably just the different n choose K formula from a few slides ago. You could rework this and get that, but
I think there's a function in R. Is it P birthday?
Oh, probably. Yeah.
Yeah.
But if you want to write it yourself and step through it in a way that makes sense, yeah, not have it happen behind the scenes. Yeah.
Cool.
And then this is one that I posted on Slack in a moment of excessive frustration last week because I just didn't get the way that it was structured in the book. And I finally, like 10 minutes before we met today, finally finished this slide. So I think I get it now. I'd probably forget it again if I had to do it from scratch. But hopefully we can go through it together really quick and then both understand it. So this is like a famous probability problem that this Pepys guy came to Newton for and was like, hey man, help me solve this gambling problem. Which of these scenarios has the highest probability? At least if you're rolling 6 fair dice, the probability that at least one of those is a 6, or 2 6s for 12 fair dice, or 3 6s for 18 fair dice. And I think most people's intuition, mine included, is that these should be probably equal. But it turns out that's not the case. It's a little bit more complicated than that. And the intuition behind it is something that I'm still working on trying to understand. But if we follow the math, we can see that it's true, that these are different probabilities. So just starting with the first scenario, we know we have 6 outcomes per dice that we can get. So that's a total of 6 to the 6th, total possible outcomes, total possible ways that we could arrange the numbers 1 through 6 on 6 dice. So we're interested, if we think about the kind of sample space, the total number of outcomes that are possible, we're interested in the subset E, some event E, that contains every event, each event having a probability of 1 over 6 to the 6th, right? That's 1 out of the 6 to the 6th possible arrangements of these 6 dice. We want the subset E summing every event where at least one die is a 6. And so again, that would be pretty complicated to count the total number of ways that that could happen. So we can again rely on computing this as 1 minus the complement, because in this case, the complement is quite a bit easier to figure out. So the complement is we don't get a single 6 on any of the dice. For this situation where we're rolling 6 fair dice, we don't get a single 6. So what's the probability of not getting a 6 on a single die?
5 out of 6 on a single die.
Yep, exactly. So from the multiplication rule, then, if we want to say like, well, what's the probability that we know it for an individual die? What's the probability that all 6 are not a 6? Well, it's 5/6 to the 6th. It's the probability of each one multiplied by the other one. So 5/6 to the 6th power.
We just love complements, and we love the multiplication rule. They're great.
Yes, we do.
Yes, yes, we do.
Yep. So therefore, if we step through that math, we get, so the probability of E complements, the probability of no 6s at all is 5/6 to the 6th. So the probability of E then, 1 minus the complement, is 1 minus 5/6 to the 6th. And that ends up being about 0.665. So are you with me so far on this one?
Yes, fantastic.
Okay, and then this is the part where the way it was written in the text kind of broke my brain. So we can step through it here, and hopefully that makes a little sense. So, because he wrote it in a slightly different format, and at first I didn't quite understand what this was going through. So we kind of took a little bit more of like a probability of, I mean, this is all probability, but like we took the probability of an individual die not being a 6, and then we use the multiplication rule to get at the solution. But this kind of like combinatorics approach, where we think about like the different combinations, it's a little bit different of a syntax. And for whatever reason, I find the previous slide more intuitive than this one, but we can go through both. So again, if we're thinking of, instead of looking at the probability of a die being not a 6, we can think, well, there's 5 possible values. And it's basically the same thing. There's 5 possible values that any of the die can take on, anything but a 6. So for E complement, there are a favorable number of outcomes of 5 to the 6th, right? So 5 outcomes for die 1, die 2, die 3 to die 6. So the probability then is again given by dividing 5 to the 6th by the total number of outcomes, 6 to the 6th. And then to get E, where we're having at least 1 6, again, it's 1 minus that. So this is for the situation where we have 6 dice. For 12 dice, now we're not, the question again, to remind you, the question was, what's the probability of getting at least 2 6s with 12 when you roll 12 dice? So now the complement of rolling 2 or more is not rolling any or rolling just 1, right? Because that would also be, so our sample space that we're interested in is at least 2 or more. So the complement would be 0 6s or 1 6. So this part is like definitely a little bit more confusing. So the first part of it holds true. It's easier to figure out, like, well, no 6s at all. There's 5 possible values that any die could take. And then we have 12 die. So 5 to the 12, that's the number of outcomes that are favorable to E complement.
Yep.
So how do we figure out the number of outcomes that are favorable to, or the number of outcomes that would give us 1 6, just exactly 1? So if we think about listing out our 12 dice and calling them die 1 through 12, we have to pick one of them, any one of them, to be a 6. And then the rest of those 11 die have 5 possibilities, right? So it's 12, we have 12 dice and we need to choose one to be a 6, right? So this would be the number of, this
Yeah.
is like the shorthand way of saying like the number of ways we can choose one from 12, which in this case is easy, it's 12. And then the rest we multiply to figure out how many other ways there are to get this. The rest
Yeah.
have 5 options of what they could be. So it's 5 to the 11 times that 12. And then again, we divide it by the total number of possible outcomes, which is we have 12 dice this time, so 6 raised to 12. And then, so this section here is the probability of the total probability of getting no 6s or just 1 6. And then to get the probability of then at least 2 6s or the complement of that, it's 1 minus it. And you can see already that this is less likely than getting 1 6 with 6 dice. And then for the 18 dice, right? So now we're interested in getting at least 3 6s with 18 dice. So 1 6 for every set of 6 dice. And that's, I think, where the mental math wants to make all these probabilities the same. But when you actually step through it, it's not. So again, like the first term is easy. The probability, the complement, right, of getting less than 3 is getting 0 6s, getting 1 6, or getting 2 6s. So 5 to the 18th, we have 5 possible values that all 18 dice could take on to give us no 6s. And then this is the same as this term here. To get 1, we have 18 dice, one of them needs to be a 6, 18 choose 1. The rest of the 17 die have 5 options. So that's the second term. And now we have another possibility that we have to count the number of ways this could happen is 18 choose 2. We're going to choose 2 dice to be a 6. And then the rest of the 16 can have any of 5 values. And then we divide that again by the total number of outcomes, which is 6 to the 18th. And then this comes out to be 0.6. So the correct answer then is that the most probable, the most likely scenario, the highest probability of rolling a 6 is with one group of 6 dice, and it does not increase. Yeah.
That's fantastic. That's really,
That one,
really, I'm so impressed.
no, I just found a YouTube video that explained it to me like 20 minutes ago. So
Well, don't worry about how, but you're there. That's really, really good.
yeah. So this one really I struggled with. I think part of it too is like the nomenclature of like 18 choose 1. Where does this 5 to the 17 come from? But the way that it was explained in that video that I just watched, that I can drop in the Slack too, if you're interested.
Cool. Yeah.
That made a lot more sense. But I think in general, like seeing this doesn't make intuitive sense to me. Like, what is that saying? Yeah. So like stepping through these is really helpful, but yeah, I struggled in the solution and the text just showed this and it didn't explain what was 5 to the 17. What did that mean? So yeah.
You're an American, you probably don't know who Samuel Pepys is.
No.
He is he's famous as a diarist, basically. The Samuel Pepys diary. He lived in London about the time of the Great Fire of London. And I think he was a member of Parliament, and he worked in the government and stuff. But his thing now that's famous is basically his diaries. So he was a bit of a man about town in 1660 or something like that.
Yeah, I had never heard of him.
But yeah, no, that's really good. So yeah.
I'm not sure how to escape now. Those are the only problems that I had for today. Yeah, and this last one in particular really threw me. So I'm glad that I found that video to explain it a little bit better. How do I get out of this? There we
go. Try escape. Is that?
Yep, that worked.
Okay. Yeah. No, that was fantastic.
Cool.
Yeah, you've done brilliantly.
Thanks.
My battery's going low. Hold on a sec. Hang on, I shall just plug this in. There we go. That's better. So, are you happy to do the chapter 2 presentation next week?
Yes,
okay?
yeah.
Yeah.
Now I have an extra week to get through it because I'm still going through a few practice ones from chapter 1, but I think I'm like finally grasping a little better. So hopefully chapter 2 is a little quicker.
No, I'm genuinely really impressed. I think you're further ahead than me. Yeah. I'm gonna try and do some chapter 2 questions for next week, and yeah, I might be crying, I might not. You know, I don't definitely say that I won't be crying, but yeah, we'll give it a go.
Yeah, I think it's probably sadly worth it to like really slow down in these early chapters and make sure that we get these like simple classic problems. Yeah.
I think doing the questions is actually how you learn it. I wish it wasn't. I wish there was an easy way to do it, but I think
yeah. Yeah. So I think it's probably going to take us a bit longer to get through this book than I had anticipated, especially if it's just going to be us two or maybe one more person joining each week. So that's okay.
Shall I advertise it a bit more?
Yeah, maybe. I told a few people I work with about it because we're all trying to learn statistics a bit better right now, but I think it's the most imminent need for me versus them. So yeah, I tried.
Cool, fantastic.
I think maybe because it's less about R and it's more about statistics and probability that people are probably shying away from it, but yeah.
And also it's really brutal as well. You know, it's a bit like, well, would you like to do 100-mile race? You know, jogging across a mountain? No, most people normally wouldn't do that. You know?
Yeah. That's okay. Hopefully, yeah. I mean, I really need to understand it for a lot of the analysis that I have to do. So it's going to be worthwhile.
Cool. That's fantastic, Chelsea. Right. I'll see you next week, and hopefully I shall have done some more homework by then.
Yes, same. All right. Have a nice day.
Take care.
See ya.